Okay, now we need to look at the pattern using two different experiments. And I noticed that between 1 and 3 there's a change here and not here. So I'm going to compare experiments 3 to experiments 1. And just so you know, I kind of rig it to where the higher numbers are on top, because it's easier for me to say 2 equals 2 to the y rather than 1/2 equals 1/2 to the y. All right, so experiment 3. Again, the rate, I'm using this. Rate equals K, concentration, concentration. So my rate in 3 is 4.92 times 10 to the negative 3 meters per second equals K times the concentration of NO, which is 0.2 molar, raised to the X power, times the concentration of hydrogen, raised to the Y power. And now I'm going to write the same stuff for experiment 1. Okay, experiment 1, the rate is 1.23 times 10 to the negative 3 molarity per second. K is K. My NO and my hydrogen are both 0.1. So once you get that written down quickly, then you simply simplify. So 4.92 over 1.23. If you divide this, you will get a 4. And if you don't get exactly 4 because you're dealing with data, like you might get 3.98, I would round that up, okay? But it should be really close to a whole number. The K's cancel. The 0.1's cancel. So here we have 0.2 over 0.1, that's 2 to the X. So now our simplified math is 2 to the what power is 4? Well, the answer is 2. So now we're ready to turn our generic rate law into the real rate law. So y was equal to 1 and x was equal to 2. And that is the generic rate law. If you're ever asked for the overall order of the reaction, then you just add the exponents. If you're asked for the order of NO, then you say the order is 2, or it's second order with respect to NO. It's first order with respect to hydrogen. Okay, once you figure out this generic rate law, you can do a lot of things. But the first thing you're going to have to do is you're going to have to solve for this K value. It is constant if you don't change the temperature. It's constant even though you're changing concentrations. So actually, you take your formula and you now use it. And just pick any of the reactions. You could do all 3, but you're going to get relatively the same number for K. Sometimes they'll have you do all 3 and average it. Most of the time, you just can just pick one. So I'm going to take my rate. I'm just going to use experiment 1. Those are easy numbers. And I've got I've got rate is, so 1.23 times 10 to the negative 3, that's my rate, equals K, that's my unknown, times my NO concentration, which for experiment 1 is 0.1. And here, I'm really going to want to make sure that I put in my units, because every K has a different kind of unit. So this is 0.1, and this tells me to square it. That's super important. And then I have my concentration of hydrogen, which is also 0.1. But my formula tells me to raise that to the first. Okay? And so that is, I simply just followed that. So now I'm just going to solve for K. I'm going to go ahead and erase this so I have room. Okay? And be careful, 0.1 times 0.1 is 0.01, times 0.1 again is 0.001, and then you have a molarity squared times a molarity again, a molarity cubed. So you just go slow. 1.23 times 10 to the negative 3 molarity per second equals K. And so now as the final step, I'm going to divide through both sides by 0.001 molarity cubed. 0.001 molarity cubed. And so, when I divide this, 0.001 is the same as 1 times 10 to the negative 3. So I actually get, as my constant, 1.23, and the units end up being, this is a molarity to the first, this is a molarity to the third. So that cancels, and this turns into a 2. So there ends up being a molarity squared in the bottom, and then the second stayed. There was nothing to cancel that out. That is actually my K value. Most people would probably write it 1.23 m to the negative 2 s to the negative 1.